class, we solved this continuous beam problem with the help of flexibility method. And as I told that in this particular problem, the question in the question there was no sinking of supports, like whether it is support C or support B or support C or support A. Okay, none of the supports were having the problem of sinking. Okay, so this is the, so if there is no sinking of support, then we will consider this and we will follow this procedure in order to find out the redundant forces, thereby to, and after that, after finding out the redundant forces and all everything, we will go for the bending moment diagram, which I told you to do it on your own since it's already been taught several times. Okay, so but in today's class we will take another problem, and that will be again the problem of a continuous beam, but here we will be having the supports will be sinking. Okay, so let me erase this one. Okay, so please take down the question. We'll directly go to the problem. Okay, so you can give the heading as analysis of beams having sinking supports using flexibility method. Okay, so let us write the problem. So the problem is analyze the continuous beam as shown in the figure below. Using flexibility method okay, full stop. The supports B and C, the supports B and C settle by 10 mm, 10 mm and 5 mm respectively. Full stop. Take EI equals to 180 into 10 to the power minus 4 Newton per mm square. Full stop. Also draw the BMD. So we have to also draw the bending moment diagram. Okay, now let's see how the structure is. So this support, this is A, this is B, this is C, and we have a load over here. This is 80 kilonewton, and we have another load over here. This is 40 kilonewton, The distance between this is 2 meters and the distance between this one is also 2 meters. This one is again 2 meters. This one is also 2 meters. And what else is given? It is given that this one is 2y, this whole span is 2y, okay, and this span is I only. Okay, now let me do this. This is BC, this is D, and this is E. Okay, now what do you think? What kind of structure is this one? Whether this is a determinate one or an indeterminate structure? Who can tell? Who can tell whether this continuous beam is a determinate structure or indeterminate structure? Anyone?
Indeterminate structure, sir.
Indeterminate. Why it is indeterminate?
Supports, sir. There are 5 supports and we have 3 equilibrium conditions only.
We have 5 support reactions, right? 5 support reactions and 3 equilibrium conditions. Okay. So the step, all of you please start writing now. So the step 1 is degree of static indeterminacy. All of you please pay attention to this class seriously, because the procedure which I am following here, it is different or little bit different from the previous class. Okay, so we all know that the degree of or the static indeterminacy, let us say RISI equals to capital R minus small r. So capital R is, how much is capital R? Capital R is, so here you can see capital R is 5 minus small r is 3. So 5 minus 3 equals to 2. So the degree of static indeterminacy is 2, right? So if this is 2, then if the degree of static indeterminacy is 2, we already know that it is, the equations are d minus dl equals to f into something, right? What is that something? F into P. Okay. So this, so since the degree of static indeterminacy is 2, this will be 2 cross 1. This will be of order 2 cross 1. This is of order 2 cross 2. This is of order 2 cross 1. Okay. Understood? So this don't write now. This is just for your reference. You will come to know, or you will find these later on. Okay. So the next step is, so if we have if we have the degree of indeterminacy, the degree of static indeterminacy 2 means, so what I told in the previous class, so if the degree of static indeterminacy is 2, then here we have either we have 2 number of reactions. It may be a force or it may be a moment which are redundant or which are extra. Okay, due to which we cannot analyze the structure directly as it is. Okay, so what we need to do, but here the case is somewhat a little bit different from the previous one, because here it is given that the support B and support C, this one sinks by 10 mm and this one sinks by 5 mm. It is already given in the question. Okay, so when the supports are sinking, then at that particular case, what you have to do, you have to take the reactions as redundants. Okay, you have to take the reactions as redundants. In the previous problem, what we did, we have taken the moment as redundant. Okay, moment as extra. Okay, so but here in this problem, what we need to do, we will take the reaction forces here as redundant. So you please take a note. So let me write the note here. So note. Now what is the note? So the note is the forces and the moments can be considered as redundants. Full stop. In this particular case as the supports are sinking, it is advisable to consider the forces at those supports, right? Not at that, at those supports as redundants. Okay, so now let us draw the diagram. Okay, once again we will draw. Let's say sorry, let us say that this is your figure A. Okay, let us say this one is figure A. Okay, we will draw another figure, that is figure B. Okay, one more thing I missed. No, this one I and 2I. I thought that I missed. That is correct, no issue. Okay, so let's draw that. So let's draw that figure once again, and this will be your figure B. Okay, this one is the fixed support. This is one support, this is one support. Here we have one externally applied load, here we have another one. So let us consider these ones. Okay, let us consider these two vertical reactions as redundants. Okay, so this one I am giving it as 1, this I am giving it as coordinate 2. Okay, so if that is the case, then how the release structure will be? So everything will come down here. So this one is the, let me increase the thickness. So here it is, the fixed one. What I have done, I have removed this reaction. So what I am saying that this one I am considering. So this is A, this is B, this is C, this is D, this is E. The distance from here to here, it is again 2 meters. From here it is again 2 meters. From here it is 2 meters. From here it is 2 meters. This is 80 kilonewton. This is 40 kilonewton. Okay. So if I remove these supports, if I remove this support at B, support at C, this will be a cantilever beam now. Instead of a continuous beam, now this has become a cantilever beam. Okay, so this is again A. This anyway we can call it as D. This is B. This is E, and this one is C. But here there are no supports now at B and C. So this one we call it as figure B, and this is the released determinate structure. Okay, and anyway this will be having loads will be here. Okay, so here we will have 80 kilonewton, and here we will have 40 kilonewton. Okay, these loads will be there. Okay, that's it. So we can write here as the redundants are RA, that is coordinate 1, and RB, that is the reaction force at coordinate as 2. I can call it 2. Okay, since I am saying this is 1, this is 2, so RA will be for this one, RB is the redundant. Okay, done. So now we have done we have found out the released or the released determinate structure. The next one is the coordinate direction. Okay, so the coordinate direction so I'm drawing here itself. I'm just extending this one. Okay, so this is the beam, this one is the fixed support, and I am saying that this one is the coordinate 1 and this one is the coordinate 2. Okay, so in this direction we will apply the unit loads in order to determine the respective moments. So let me write, this is A, this is B, this is C, this is E, sorry, this is D, and this is E. Okay, this is the, so this figure is the coordinate. So this is figure C, and figure C is the coordinate directions. Okay, so next step is step 2. Okay, step 2 is, so we know that from unit load method we know that this delta or theta, whatever we want, delta or theta equals to integration 0 to L m into small m into dx by EI. Now what is this M? So this M is the respective bending moment due to the externally applied loads and this M, small m, is the bending moment due to the unit loads. Okay, you will understand, you please pay attention now, you will understand in a moment what I mean to say. Okay, so just now what we need to do, I will make a table. Okay, so the first one in the table, the first one will be segment, then next is origin, next one is limits, next one is EI value or EI variation, next one is this capital M, and this capital M I will tell you from where you will get. And next one, since we have this capital M is for this one, and next one is small m, but here since we have two redundants, okay, so depending upon the redundants, the small m value, number of small m's will be there. So this is small m1, this is small m2, since we have two redundants over here. Okay, so let me this much will not be required, I guess. So let me draw the structure here once again now. Okay, so the structure is like this now. So this is A and this is E, this is B, this is sorry, not this, this is not D, this is D, this is D, this is E, and this is C. This is the structure now. Okay, and at D we have, at D and E we have the loading. So here I have this one is 80 kilonewton, this one is 40 kilonewton, this is 2 meters, this one is again 2 meters, this one is 2 meters, and this one is 2 meters. Okay, and this is 2i, this segment A to B, and this one from here to here it is 1i. Okay, or I, whatever you may call. Okay, so now, so how many number of segments are there? So let us consider from left to right. Let us consider from sorry, let us consider from right to left. Okay, so the first member is CE, the second one is EB, the third one is BD, and the fourth one is DA. Okay, so I will write it here. So I'll write it here as this is the first one is so the first one is EC, sorry, not EC, I'll follow CE, then EB, then BD, then DA. Okay, and let us say that the origin for each segment is the first one. So let us say for CE the origin is C. Okay, then let us say E is the origin for BE. Let us say B is the origin for BD. Let us say D is the origin for DE. Okay. Now the limits is for the limits is means the length. Okay. This is 2 meters. So this one can be 0 to 2. Again this one EB is again 2 meters. So the limits is 0 to 2. Then for BD the limit is again 0 to 2. For DA again the limit is 0 to 2. Okay. Now the EI value for this one, the for EC and EB, the EI is 1 only. Okay, so EI I can write it as how many times it is 1. So EI is 1 here and EI is 1 here, and for this one EI is 2 again. This is 2. Okay, so now from where we will get the value of M and M1. Okay, so we will get the value of M1 from figure B. Sorry, not here. We will get the value of M from figure B. We will get the value of small m1 from figure D, and we will get the value of small m2 from figure E. Okay. So now all of you please pay attention now. This is very crucial now. Okay. So let us say again this figure. Okay. So what I'll do, M is the moment due to the external loads. Okay. So for this segment, let us say I consider X from this direction. This is X. Okay. I'm considering this section. Okay. So moment in this from C to E, from moment at this section, what will be the moment at section? Any external force is there? Only I'm always taking from right to left. I'm always going from right to left. If I'm going from right to left, any value is there? Any reaction force is there within this C to E, in between C to E? No, right? So now, so this M will be 0. Okay. Now, what I will do? I will take the next section. Okay. I'll take the next section, that is EB. EB. I'm taking this section EB and I'm making, I will have to find out the moment at, let us say, x distance from EB. Okay, EB. So here it is 40. This external applied load is there. This one is already there. So this one is 40. So 40 into x, and this one is again in the clockwise direction. So let us say I am taking this one as minus 40 into x, minus 40 into x. Okay, now let us take the section BD. Okay, so I am removing this one. So now I am considering section BD, and section BD, let us say I am taking x distance from B. Okay, I am taking x distance from B. Okay, so do we have a force here? No, but we have a force that is 40 kilonewton, which is at a distance how much? This is x from here to here. This is again 2 meters. Okay, so it will be 40 into, so minus 40 into x plus 2, minus 40 into x plus 2. Okay, so similarly, if I take the other section, I'm removing this one. This is E. I'm considering section here. Okay, this is again, it is 2 meters. So if I'm considering x here, okay, so what will be this value? So again, I have two forces, that is, this is one, okay, that is 80. So 80 into x plus 40 into x plus 4, this is x. This is 2 meters plus this is 2 meters. So minus 80 into x minus 40 into x plus 4. Okay. Now for M1 we need to consider this figure. So this is A, this one, this is E, this is B, this is E, and sorry, this is D, this is D, this is D, and this is C. Okay, this is again, this length is 2 meters, this is 2 meters, this is 2 meters, and this is 2 meters. Okay, so what we have considered here, or at this point we have considered, let me change the ink. So at this point, this is our coordinate 1. Okay, so I am applying 1 kilonewton here. Please remember 1 kilonewton here, not moment. I am applying a force 1 kilonewton here. Okay, I am applying 1 kilonewton here, And now again I need to find out the small m1, small m2, sorry, small m1 here, here, here. So at every section I need to find out what is the value of the moment. Okay, so now if I take this section, and I told you that I'm always going from right to left. Okay, so if I take this section, I'm taking this x. Okay, so moment at this point, is there any force here? See, now we are not bothered about this one and this one, externally applied force. No, we are not bothered about this one. Now we are only bothered about this one, this 1 kilonewton unit load which I have applied now. Okay, so due to this 1 kilonewton, any change moment will be there here? No, because I'm considering this section, and in between this one there is we don't have this load. Okay, so this will be again 0. This will be 0. Okay, so similarly, if I consider section this, if I consider this section, I'm removing this one. This is E. I'm considering section here, X. Let's say X. This is B. Okay. So here, if again I'm considering, there will not be any value over here. Now, if I consider a section here, if I consider a section here, then definitely this 1 kilonewton one will have some value, that is 1 into x. So that I can write as 1 into x. Okay, so now if I take a section here, and I have the load here as 1 unit load, that is 1 kilonewton. Okay, and this one is x, let us say. So this one we already know, this is 2 meters, this is 2 meters, and this one is 2 meters. We already know this one. So this will be 1 into x plus 2. Okay, 1 into x plus 2. Okay, so similarly we will finish this one. We will just finish this one, and later in the next class we'll continue. So this is you may be a coordinate 1. Okay, we have applied unit load at 1. So now we will apply unit load at coordinate 2. Okay, so this is A, this is D, this is E, this is B, this is E, and this is C. And here I am applying 1 unit load. I am applying 1 kilonewton unit load here. I am removing this one. Okay, so if I apply unit load here, then if I take section from here as x, then this is by default, it is 2 meters, this is 2 meters, this one is 2 meters, and this one is 2 meters. Okay, so this will be x into, or 1 into x. Okay, so I'm writing it 1 into x. Then if I take a section here, if I take a section here, then this will be 1 into x plus 2, because this one is this one, it is 2 meters by default. This is 2, so 1 into x plus 2. So 1 into x plus 2, 1 into x plus 2. Okay. Similarly, if I will consider a section here, then this will be 1 into x plus 4, and if I consider a section here, then 1 into x plus 6. Okay. So this is the table which we have to determine in step number 2. Okay. So any doubts in between till now? I am stopping the recording here.